don't have V4 nice.
Okay, so yeah, the dynamic has changed. Okay, so we'll settle in. Okay, so here's what we have in the second half.
Did you get a haircut? Yes.
I did.
Oh, I did.
Thanks. I was telling Louis I was like in Louis mode. I was just getting a little out of control with him. So take this for what it's worth. I actually had a dream with Pop and Louis last night. It was the weirdest dream. No, true story. Like, we were walking down the street and there was like this big drift of snow, and it was like a open deuce coupe car, and we're sitting on top of it. And Pop, for whatever reason, you decided to push the car off the drift. But when you did, like all the wheels literally fell off. And it's like, what are we going to do? It's like we pushed the car and the wheels fell off. And Louis goes, oh, Burkamp, let's weld it back on. So for some reason, I'm not sure why, there was a welder. And we started like welding the wheels back on the car. And then you started smoking cigarettes. And I said, Louis, what are you doing? He's like, hey, I'm a welder. I want to look like a welder. You're smoking on cigarettes. I'm going, okay, that was just kind of weird. So, yeah. It was weird. But, hey, we got the car. It was cool when we got done. So, other than Louis standing there smoking a cigarette. So
That was a weird dream.
yeah, sitting on top of the snowbank. Okay, so here's what we have in terms of the second half. And for those of you that are transferring in, everything we're going to start is new to everyone here. Okay, so don't flip out and go, oh, we didn't. Look, you guys have the same knowledge as these guys do in terms of where we're starting off. Okay, so the first unit is on oscillations, which is going to be chapter 14 out of your book. So we're actually going to start with a lab, kind of refresh a bunch of stuff that we learned, talk about energies, we're going to talk about motion, we're going to talk about acceleration, that type of thing. And then that first test is going to be a week from tomorrow. Okay, it's going to be one of our shortest units, and that's going to be a week from tomorrow. So that'll be the first test over that chapter 14. And then from there, because oscillations are basically going to form the basis of what we're going to use then to study sound. And then from that, we're going to study light. And then from that, we're going to get into optics. So oscillations kind of form the basis of what we're going to do next, because if you look at how sound works, if you look at how light works, basically it's making things oscillate. So this is why we study oscillations, or we're going to use a spring to model that, to form the basis of how we're going to then, how can we apply that same matrix to a sound wave? How can we apply that same matrix then to a light? And so that's the whole basis of that. So from there, we're going to get into electric fields. From there, we're going to get into circuits. From circuits, we're going to get into magnetism. And then from magnetism, we're going to get into the last unit on nuclear. And that's where we're going to end up. So that's kind of like the big picture in terms of the sequence. And so this first unit that we're going to do on oscillations, there's not very many units on, or very many formulas on any of these. For those of you that don't flip out and go, some of these equations aren't on here. Some of these oscillation equations are very specific, and I will always give those to you if they're not on the sheet. Okay, so don't worry about necessarily memorizing them, like we're going to get into like maximum accelerations and things like that. So the ones that we're going to use that's on here is this x equals a cosine 2 pi frequency times t, and then this omega equals omega naught plus alpha t. Those are the only ones that are really specific to this unit. There's going to be a whole bunch more that we're going to develop as we go along. So I like this first lab because it's going to tie together some things that we covered before, and I'm assuming that you all have offloaded a lot of information that we had before over Christmas break. So the first thing that we need to do, you're going to set up a set of rings like this. And the first thing we need to figure out is the value of the spring constant, because we're going to use that to do everything else. So when you do that, when you set up this graph, and we're only going to do 2 points. We're going to use a half a kilogram one, we're going to use 1 kilogram. So remember, you got to put your force here, and you got to put your elongation here. You're gonna have a couple of points, boom. You're gonna draw a line of best fit, okay? Remember, this is what's known as Hooke's law, basically says the force is proportional to your elongation. So you're gonna work off this idea that F equals Kx. All this is a linear function.
Sideways.
Huh?
Sorry, I was confused on what your Y was.
Oh yeah, that's force.
Okay.
Can't you read that as force?
No.
If you hadn't spent so much time smoking cigarettes, you would realize this.
habit.
I know. So,
Hard to budge.
there's force.
That still doesn't work.
Okay, it's close enough. Y'all read my handwriting right now. So it's a linear function, F equals Kx. So you're gonna have 2 points, draw a line of best fit. You know the drill. Show me how you calculate this. So that K value is going to be that spring constant. Okay, so all this is a linear function. Force on the y-axis, here's gonna be your elongation. So you gotta do that before you do anything else. So once you get that done, and then you're gonna take 1.5 kilograms, like so.
It's gonna take
Oh, come on. Thank you for that vote of confidence. Okay.
It's very tempting, Sam. It is. Trust me.
So what you're gonna do, and make sure that you clamp this down so that it doesn't go doink. So you're gonna make this oscillate. So when you talk about springs, you need to talk about, we need to introduce some new terminology. So one of them is what we're gonna call the amplitude. So your amplitude is going to be how far it moves from its equilibrium point. If you're talking about a sound wave, basically your amplitude determines the intensity of the sound. If you're talking about light, your amplitude is a reflection of almost like the intensity of light. So amplitude is basically how far that wave moves from the middle. So when this thing is oscillating, what you want to do is get it oscillating, and then what you're going to do is that you're going to have the middle ring where it's at its equilibrium point. So you're going to have the middle ring like this, okay? And you're actually going to get down and make sure that's right there, okay? And then you're going to make it oscillate. And then you're going to have the bottom ring, oddly enough, at the bottom of the oscillation, like so. And then you're going to have this ring at the top of the oscillation, okay? And so that should be pretty symmetrical where you have that same distance up and down. So in terms of what you're going to measure, the first thing you're going to do is you're going to find the spring constant. You're going to hook up you're going to hook up a 0.5 kilogram mass. You're going to measure how far it stretches. You're going to hook up then you're going to put a 1 kilogram on there. You're going to measure that, get those values. Louis,
Have we already done this before?
you have.
Oh, okay. Wait, sorry. I was.
No, you have, okay? But different springs have different spring constants, and you have to know what the K value is for that particular spring. Because we're gonna use that later on, okay? So your spring constant is we're gonna compare that to a different way of calculating K, but we need this as like a reference, okay? So when you talk about this thing oscillating back and forth, so quick refresher. Is the mass accelerating?
Yes.
Yes. Why?
Because it is going from 0 to speed. And then
It's changing direction.
Okay? So what we're going to do is that we're going to look at a graph. We're going to have 3 different graphs. A position versus time, a velocity versus time, and an acceleration versus time. Okay? So let's even go back farther. If something is speeding up, what do you know about the sign of velocity and acceleration? Same. Something slowing down, it's opposite. So what we're going to do is work in this lab, and I laid this out in the lab itself. We're going to define up as being positive, we're going to define down as being negative. We're going to define if this is, so here's this equilibrium point. So if it's above the equilibrium point, it's going to have a positive position. If it's below that equilibrium point, it's going to have a negative position. So we're going to go from, what we're going to do is we're going to assume that this thing is starting up at the top, and then it's going to fall, stop, boom, change direction, and go back up. So we're going to have three different types of energy as well. So when we started this analysis, if we're going to do like a position time graph, we're going to start it up here at some positive position. So as soon as I let go of that, that begins to oscillate. As it falls, what's my position? And here's 0. Here's that equilibrium point. And then it's going to have some negative position. So you're going to start up there. So as soon as it falls, what's that going to do?
Go down.
It's going to go down, right? So it's going to go through 0, and then what's it going to do?
Keep going.
Down to some negative value, then what's it going to do?
Go back zero.
It's going to go back up, like this, right? So one way that you can visualize this, and some people like this idea, is that imagine that I'm going to attach a pin to this, okay? And this pin is going to move with this spring. So imagine this is going back and forth like this. And then I'm going to drag a piece of paper that's going across that. So imagine that here's my pin. I'm starting up here at the top. And then as that falls, I'm going to drag that piece of paper, and so that paper, as it moves, is going to have this wave that's going to be transposed onto it. Okay? So if you like that visual, it's like, oh yeah, here's a pin. And that pin's going to be going back and forth. I'm going to be moving this piece of paper across with it. If you like that visual, that's cool. Now, so your position time graph is going to start up there at the top. So since it's starting at the top, what's its initial velocity going to be? No.
Sorry, the initial?
Initial.
0.
It's going to be 0, right? So when I look at my velocity time graph is going to start at 0, okay? Because it's at the top. So how much kinetic energy does it have at the top? 0, because it doesn't have any velocity, right? What type of energy does it have? It has UG, right? Because remember, UG is mgh, right? So we have some UG. Okay.
Spring energy.
Oh, we also have some us, right? So why do we have us?
Because it's a line.
Because the string is stretched, and remember, us is 1/2 kx squared, right? So even though it's at the top of the oscillation, we still have some us because the spring is still stretched. So you have us, UG, and you have KT, right? So when is your KT going to be at a minimum? At the top and the
Bottom.
because you are changing directions. What three things does an object have to do to change direction? Slow down, stop, and speed back up. Okay? So is this thing, if you could watch that in slow motion, on that way up it's slowing down, it stops, boom, begins to speed back up. So when do you think it has its maximum kinetic energy?
At the middle.
In the middle, because it speeds up till it hits the middle, and then it's going to start to slow down. Okay?
Decelerate.
Really?
Sorry.
Really? First?
Get back into it.
No. Okay. So, if you look at F equals Kx, so what are the two forces involved that are acting on that spring as it oscillates? Obviously, you have the force from the spring.
There's gravity.
You have gravity. Fg equals
MG.
mg. Thank God someone knew that. Okay?
No problem.
Gravity? We haven't talked about that before. Wow. Okay? So, as it oscillates, what happens to the value of your gravitational force?
It stays the same.
Stays the same. Okay? It's not going to change. Does the force from the spring change?
Yes.
Yes. So the farther it stretches, what happens to the force from the spring?
Increases.
Increases. So basically what's happening is that this is a force tug of war. So when it's up at the top, right, your gravitational force is stronger. That's why it begins to fall. So then you can talk about net force. Oh, right, that's an imbalanced force. So it begins to fall, and because the gravitational force is greater than the force from the spring. Then as it stretches, what happens to the force from the spring? It increases until that eventually reaches a point where it's bigger than gravitational force. That's why it stops, and then it makes it go back up. But then as it goes up, what happens to the force from the spring? It becomes less, gravity becomes stronger, it slows it, it makes it stop. So even though your gravitational force is the same all the time, the force from the spring is continuously changing. So that's what allows it to oscillate. So you have a whole bunch of dynamics that are taking place. You have forces that are continuously changing. You also have forces that are remaining constant. You have energies that are changing, okay? Us, UG, and kinetic, okay? So you have that dynamic that's always changing. But no matter what, if I let this thing oscillate, eventually what's going to happen?
It's going to stop.
It's going to stop, right? It's going to come to a stop. So what that means is that energy has changed form. So what's happening over the period of time is that as that's making on an atomic level, as those atoms are being stretched and then pulled back together, that's generating a small amount of thermal energy. Now it isn't like, wow, it's cold outside, let's make a spring oscillate back and forth, that'll warm us up, okay? It's not what's going to happen. But on an atomic level it is, okay? Because anytime you make particles move out of their equilibrium position, they get frustrated and they're like, oh, okay? And then they give off energy in the form of heat. So that's why this thing is eventually going to come to a stop. Okay, so let me hand out the first page of the lab. There's actually going to, we're going to start this today, and it's going to take us like 2 days to get through this. So this is just the first salvo.
Let's go. Go.
That's good news. Lab days are all.
Yeah, good news.
You were not writing a paper.
5 minutes.
What class?
English.
Peterson.
Peterson? You have second ball?
Mr. Burkamp?
Okay. What?
Sorry.
What?
I'm a little confused on F equals KX.
Okay.
Why is F equals KX and US is 1/2 KX squared?
So here's the
Like,
short
how do you
version.
get to there?
So force, elongation, okay? So this slope, F equals KX, right?
Yeah.
Base linear function. So if you were to find this area underneath here, okay? So that area is 1/2 base times height, right? Which is 1/2 my base, which is my elongation, times my height, which is force, okay? But if I substitute KX in here, then I have 1/2 X times KX, which becomes 1/2 KX squared,
There you go.
Oh, okay, cool, gotcha.
okay? Now, if you're a calc nerd, if you take the integral of a linear function of kx and you raise that to x squared and you put the 1/2 in front of it, if you've taken calculus, that's the short version of it, okay? When you evaluate an integral in between 2 points and you raise the exponent by 1 and you put the fraction out in front, okay?
Oh, okay.
There's the short version of the fundamental theorem of calculus. Don't worry about it. So you can either prove it from an algebraic standpoint or you can do the calculus. But that's why that works.
Okay.
Yes.
Since we're on questions,
Yeah.
what were you saying when you said the force of gravity was making it stop because it became larger?
No. It's
Gas or
relative to
something?
the force from the spring. So right now, when this thing stops oscillating, okay,
Yeah.
you have gravity pulling down, and you have the force from the spring acting up. Okay, so right now everything's in equilibrium. But the force from that spring is F equals kx, okay? So the farther I stretch that spring, the more upward force there is. And the less it's stretched, the lower the amount of force.
Oh, okay.
So when that thing's at its top, you have your smallest amount of force from the spring, but gravity is still pulling it down, okay? So when you reach the top, the gravitational force is bigger than the force from the spring, therefore it falls down.
Oh, okay.
But when it hits the bottom, the force from the spring is bigger than the gravitational force, and that's what makes it move up. But when you're at that equilibrium point, the two forces are balanced out. Okay? Makes sense. Okay. So, what you're going to do is, and you can, I'll just cut some graph paper in half. Yes, everybody does their own graph. Simple point, you're going to have 2 points. You're going to have 0.5 kilogram, and you're going to have 1 kilogram. So help me, do not ask me, how do we get mass into force, Mr. Burkham? So help me, you ask me that question, I will flip out. So, what you want to do is, this is where it's going to involve timing. Okay, so this is what we haven't done with this lab before. So, when you talk about this oscillation, so here's your spring, there's your mass, okay? And it's going to go from top down to the bottom and back up. So this is what we're going to talk about, pendulums, and we're going to talk about things that oscillate back and forth. So over here, you've got, I got to find it. Might be on the yellow sheet. Ah, here. Okay. So on this yellow sheet, okay, over here, we're underneath the mechanics section. So here are the equations that we're going to be dealing with. You have, this is going to be what we're going to use on this lab, which is 2 pi times the square root of m over k. And then you have the period of a pendulum, which is 2 pi times the square root of L over G. So this is a new equation that you all haven't worked with before, but
Is that
haven't
length?
oscillations yet. Huh?
Is that L length?
Yeah.
No,
Yeah, it's not angular momentum.
It's angular momentum.
Yes, it is not angular momentum, really. Okay, that is just
Use your
length.
brain.
So this is what we're going to deal with the lab today. So what you want to do is you're going to compare 2 different things. You can compare like a theoretical value and an experimental value. So what you want to do is get it oscillating, okay, like this, and then you're going to measure the time for 5 oscillations. So you're going to go, you can either start at the top or the bottom. That's usually the easiest. Okay, you're going to go, boom, 1. Now, usually if you screw this up, it's coming down to the counting part of it. So remember, you want the time for 5 complete oscillations. So start it, and then that's 1, 2. So in other words, don't start it, your stopwatch, and go 1, 2. You have to count that oscillation, okay? So get it coming down like that, boom, count 5. So on this front here, where you're going to have the time for 5 oscillations, whatever that is. It's typically about 5 seconds each period. Typically on these springs, it's about 1 second. So then you're going to have the period for 1 oscillation. Okay, take the time, divide it by 5. It's not a big deal. Then you need frequency. So remember, period and frequency are inverses of each other. Okay, so and it makes sense. So if I take this rubber stopper and I swing it around very slowly, okay, that's going to have a relatively long amount of time for 1 revolution. Okay, so that's going to have a relatively long period. But you're not going to see that rubber stopper go by very often. So this has a long period, but a low frequency. But if I make it go faster, okay, then what happens to the value of t? it becomes less, but what happens to the number of times it goes around per second?
It increases.
It increases. So that's why these are inverses of each other. So, and this is going to play out large later on. So you have period equals 1 over frequency, which means frequency equals 1 over t. So what you can also do is then come in here, and we'll go through the math later. But you can also express this in terms of frequency. So if you come in here and say, well, period is 1 over frequency, then if you take the inverse of all of that, then you end up with the exact same thing. But we'll deal with that more later on. So what you're going to do is that you're going to measure 5 oscillations. You're going to write that time. You're going to divide it by 5, get the time for 1. Then you're going to take the inverse of that, and then you're going to get the frequency. So over on page 2, okay? And I give the instructions at the bottom of page 1. So over here on page 2, you're going to, up here, you're going to draw period, whatever that period is, okay? And what I've done here is a technique that we use a lot when you talk about graphs. So you're going to look at a fourth of an oscillation, half, 3/4 t. So I want everybody to be cool with this visualization. So if I'm going to start up here at time 0, so that first graph of amplitude versus time is going to start up there at that top. So we're going to start this at the top of the oscillation, and that's going to be defined as a positive value. So then it's going to fall down like this, hit the bottom, boom, and then it's going to come back up. So when you look at this, if you go from here down to here, back to there, what portion of the period does it take to get to the bottom of the oscillation? Is that a fourth of the oscillation? Is that a fourth t, half t, 3/4 t, or the full t? Half t, because the full t gets you from here down, back up. So at a half a t is when you're all the way down here. So at a quarter t, oddly enough, you're about right here. Half the t, you're here. 3/4 t, you're back to here. Full t, you're back to that point. Okay? So you're going to have this nice, do not draw, this is like points, you're not drawing V's, okay? These are like sine waves and cosine waves, okay? These aren't linear functions. So you know that this is t over 4. So I don't care what the value of t is. So this is why we draw graphs like this. So we don't actually have to have the actual times. We just know at 1/4 t, it's going to be at that equilibrium point. At t over 2, that's when it's going to be at the bottom of the oscillation. At 3/4 t is going to go back up, and then at t, it's going to be back at the top. So that's what that graph is going to look like. Now, again, go old school. This is fundamentally, even though we call it an amplitude versus time graph, at the end of the day, it's a position versus time graph. So what does the slope of a position time graph give you? Velocity, right? So, or if you're a calculus nerd, so up here, if I were to come in here and draw that tangent line at time 0, what do you think the slope of that tangent line would be?
0.
0 would be a horizontal line. So my velocity time graph then starts at 0. So basically, if you take the derivative of all the points up here, or if you think about drawing tangent lines, those tangent lines then give you what your velocities are. Now, an interesting thing happens. Up to this point, okay, what's the numeric, I don't care about the numeric values. Up to that point, right here, what's the sign of my velocity?
Negative.
Negative. Why? There's two reasons why it has a negative value.
It's going down.
It's going down, and we're defining down as being negative. Okay, there's your most obvious answer. Okay. What about your tangent lines?
They decrease.
No. Just talk about sign.
They're all negative.
They're all negative. Okay, if you come in here and you draw tangent lines at any point along there, any tangent line up to the point that it hits the bottom has a negative value. Okay, right. Okay, so guess what? You're going to have negative velocities. When you hit the bottom here and you draw another tangent line, what's that velocity going to be? 0, because you are at the bottom of the oscillation. You're going to change direction. Now, after that point, when you start drawing tangent lines, then the tangent lines are going to be because now you're going up. Okay, so that's what you want to think through. How does that position time graph drive your velocity time graph? Now let's talk about the acceleration graph. Like, oh, Burkamp, you're killing me, man. This is a lot from the first day. Got this stuff. So when I drop it, does it accelerate? When it's at the top of that oscillation, okay,
Yes. Yes.
and it begins to fall, is it accelerating?
Yes.
Yes. How do you know? Velocity vectors are getting bigger. Okay? So as this thing begins to fall, okay, so here you are at the top of that oscillation. Okay? You're at the very top of the oscillation. When it begins to fall, which direction are your velocity vectors pointing? Downward. So you're going to have some negative velocity. As it falls, what's going to happen to the magnitude of that velocity vector?
It's going to decrease.
No.
Get bigger.
Initially, it's going to get
Bigger.
bigger, right?
Yeah.
So initially, you're going to have negative velocity vectors, which are getting bigger. So which direction are your acceleration vectors going to point at that time? Up or down? Down. Because remember, if something's speeding up, what do you know about velocity and acceleration? The same sign. So initially, you're going to have some negative acceleration vectors. Oh, okay, that's kind of cool, right? Now, maybe you've seen this equation before. Force net equals mass times acceleration. Seen that one before?
Maybe.
What little bit. So as it falls, what's the sign of your acceleration? Initially. Negative. Initially, I'm going to have some negative acceleration. True?
Yeah.
So what's the only way that can happen? Is if I have a negative net force. We're defining it down as being negative. So what's creating the negative net force? Gravity, which is bigger than the spring. Okay. We reach the middle. Once it crosses the middle, what do your velocity vectors begin to do? Louis, now what do my velocity vectors begin to do?
Oh, what?
Once it crosses, so it start up here,
Yeah.
it's falling and speeding up, reaches its maximum velocity.
Yeah.
Once it crosses that equilibrium point, what does it begin to do?
Slow down.
So then my velocity vectors become smaller. So then, after it reaches that equilibrium point, my velocity vectors are still negative, but they're becoming smaller. So I still have negative velocity, but my velocity vectors are getting smaller, which means now my acceleration vectors are pointing upward. So then I'm going to have positive acceleration. Here's an interesting idea. At some point, do I have no acceleration?
Yes.
Yes.
I got to, because I go from negative acceleration to positive acceleration. So when do you think I don't have any acceleration? The equilibrium point. Because at the equilibrium point, there's no net force because the forces balance each other out. So this looks simple, but it's actually a very dynamic situation. So here's the deal. So when you talk about your acceleration vector, when you talk about your acceleration time graph, and that's something we've never talked about. We've never talked about an acceleration time graph. Okay? Now, so your velocity time graph is going to start at 0, and then it's going to fall, so your velocity time graph is going to be gaining some negative velocity, and it's going to go something like this. Okay? So that's what my velocity time graph is going to do. Now, here's what I want you to think through. If you take the tangent lines of a position time graph, the slope of tangent lines of position time graph gives you velocity. So if you were to take the slopes of your velocity time graph and draw tangent lines, what do you think that would give you?
Acceleration.
Your acceleration. So anytime you come to a velocity time graph and you can draw a horizontal line, what do you think the acceleration is at that point?
0.
Okay? So this is where they all build off of each other. So, again, you're not going to know the actual times, okay? In terms of this is a generic in terms of 4th T, half T, 3/4 T, and T. So here's where you're going to begin to actually compare things. So over here at the top of page 3. So what I've done is I've given you the formula for the period of a spring. So you have T equals 2 pi times the square root of m over k. Now, let's go old school. Let's go old school dimensional analysis, okay? So m obviously is going to be in kilograms. Now, k is going to be your spring constant, right? So your spring constant has what units?
So from
Newtons,
per meter.
newtons per meter, right?
Yeah, that's what I meant.
So instead of newtons, I can put what? Kilograms, meters per
Second squared.
divided by
Meters.
meters. It's kind of cool. So what's going to happen to my kilograms?
They're gonna cancel out.
They're going to cancel out. I'm going to cancel out my meters. I have the square root of 1 over second squared, which becomes the square root of,
Second squared.
which is what period is measured in. Okay? So that's why it has to be m over k, because that's the only way your units can work out. So what you're going to do is you're going to take this equation, and one of the things I'm going to ask you to do 2 things. I want you to solve that equation for k. So this is just an algebra problem. I want you to go through and I want you to manipulate that equation. Don't not put any numbers. Okay? So one of the things I want you to say, k is going to equal blank, just out of these variables. Okay? Let me give you a hint. Get rid of the radical. Okay? And then here's the most common mistake. Whoa, it's weird. Okay? Don't forget to square the 2 pi. Okay, the most common mistake that's made. You forget to square the 2 pi.
Wait, why do you?
Because you do t over 2 pi, and then you have to square it. So you have to divide
Oh,
by
okay.
2
Oh.
pi.
Yeah, we're going to get rid of radical. Okay, so don't forget to square the 2 pi. So when you get done, you're going to say k equals something. Okay, just in terms of variables. Then, at this point, you're going to know the period because you measured that previously. Okay? You're going to know what the mass is. It's going to be the 1.5 kilograms because that's what you're making oscillate. And then you're going to find another way of solving for k. Okay, so at this point, what I want you to see, and this is what's new. Before, the only way we found k was to draw the graph. Oh, force and elongation, we find the slope, boom. Okay? So this is a different way to measure k that's only dependent upon the period of the oscillation and mass. Now, here's an interesting thing. If you were to go to the moon and you were to draw a force and elongation graph, if this is your line on the Earth, what would that line look like on the moon? More steep, less steep, same.
Exact same.
Exact same. Why?
Because the same
Because
force
it's
is
nothing to
being
do with
applied,
gravity.
and force equals kx, and k is constant.
But would it change at all?
Not at all.
If you use 1 kilogram and a half a kilogram.
Oh, I have a feeling it changes.
Well, okay. Well,
In other words, here's the story.
no,
Visualize
because X
this.
is elongation.
Hold on, whoa, 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 whoa,
Oh,
whoa.
because the force is
Okay.
different on the moon.
Did you just say the D word?
That's my favorite word.
I know. Guess what I hate?
The The D word. The D word. This method.
I don't care.
Okay.
I got it.
Bob,
Okay, so it still takes the same amount of force to get the same elongation, but it's just it's like the moon more mass has less force. It's less force, you know.
hold on.
You know what I mean?
I know what you're saying, but let's
The
change it up.
acceleration's
You're changing too many things, Bob.
Oh,
Okay. So this is what this looks like on the Earth, right? So you would have a force of 9.8 newtons, right?
Yeah.
And an elongation of, say, 20 centimeters,
Yeah.
right?
Mm-hmm.
Now, if I go to the moon,
Do 9 point.
I put that 1.5. I put that that 1 kilogram mass on there, exact same mass. But is it going to weigh the same?
It's
No.
gonna be 4.9.
Is it going to weigh more or less on the moon?
Less.
Less.
It's going to weigh less. So now it would only stretch it like
That much.
this much.
But it's still.
So it's still the same. It's
So-
still on that line.
No, it's still
No, it's
on the
steeper.
line. No,
It would still be on that line, right?
Yeah.
But it would change proportionally to a smaller values.
Yeah.
So the points would be closer together.
Yeah.
But it would still be the exact same slope because it's still the same ratio of force to
You did.
elongation. Now here's the interesting thing that we have. You take this to the moon
no.
and I make it oscillate. Okay? I take it to the moon, I make it oscillate. Exact same situation. What's going to happen to the period of the oscillation?
Less mass.
I take that 1 kilogram mass. Imagine this.
Oh.
We're now on the moon.
Oh.
And I make that oscillate. What's going to happen to the value of t? Will it increase, decrease, or stay the
It's
same?
gonna be
Stay
the
the
exact same.
It's gonna decrease,
Why, Louis?
because it has to travel less distance.
It's gonna be the exact same.
Sam, you think it's the exact same. Why?
Because the T equals 2 pi squared root of m over k. And if the mass is the same and the k is the same, or is the k not the same? Is the k different?
The K is.
K's the
K
same.
is the same.
So it is the same.
Oh,
So it's the
it is
exact same.
Well, you're 0 for 2.
Oh.
Okay? So, this is one of the things that you have to begin to look at. Okay?
I'm sorry.
When you look at this equation of
It's actually wet. It's very
t equals 2 pi m over k, is there any way to put the gravitational acceleration in that equation?
Nope.
No. Now, obviously, you have to, it is predicated on the idea that you have to have a gravitational field.
I was thinking-
Because if there's no gravity and I pull it down and let go of it, what's it going to do? It's just going to go up. Now, you can set it up where you have like a horizontal oscillation. So if I set it up horizontally and I stretch the spring, then you would see it oscillate back and forth horizontally. So you could have a horizontal motion that would be the exact same. Now, Louis,
Yes,
Louis.
absolutely. But
Louis, you with me? Okay? Here's the period of a pendulum. 2 pi times the square root of L over G.
yeah, that's what I was thinking of last.
Okay, I know. So now, I have this action going on here, right?
Yeah.
Okay? So, when this is up here, what type of energy does it store?
Potential.
When it's at the bottom, it's all KT. Now, so I could go through, and if I knew the length of that pendulum, not the angular momentum, if I knew the length, and I knew what G is on the Earth, I could predict the value of T, right? LG, boom, square root, we're off to the races, right? If I go to the moon, and I do this, Louis, I go to the moon,
Uh-oh.
everything stays the same length, okay? I go to the moon and I do this. What's going to happen to the value of T?
Let's go.
Increase, decrease, or stay the same?
Let's go, man. Academic weapon.
All you.
It's gonna increase
Why?
because G is on the bottom.
And you're dividing by a,
Smaller number.
so therefore, period is going to get
It's
larger.
gonna go larger.
Good stuff.
Now, here's an interesting idea.
Really crumble.
I take this mass and I make it oscillate like this, okay? Very small amplitude, okay? Then I change it
Give it a concussion.
and I get a bigger amplitude, what happens to the value of t?
It stays the exact same.
That stays the same.
Stays the exact same.
The
Why?
exact same because M and K are the same.
Because time is not a thing.
Oh, time's the thing.
No, time,
Because
you can't plug in. the
Force
amount
is
of time.
not a thing.
No,
Force
what's
is-
not a thing is your amplitude.
Yeah.
The amplitude
Okay.
is not a thing.
So how much it oscillates isn't there. So if I have this, or if I have this,
It's the exact
exact
same.
same. Now, but what does change?
Frequency
Frequency changes.
and force.
Does frequency change?
No.
Yes.
Frequency doesn't change.
Frequency changes, right?
Nope.
It's the
Just
inverse.
Because period is frequency is the inverse of
Oh,
period.
yo, frequency doesn't change.
Frequency doesn't change.
Stays the same.
Does velocity change?
Yes.
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 Velocity changes.
Because obviously that's going to be going a lot faster than
Yeah.
that. It has to be going faster to produce the same
Time.
time
Period.
because you have a greater distance to travel.
So
Okay.
acceleration
Boom.
and the force.
Okay. Now,
I'll just come in this.
when do you store more energy? When you have a little bit of oscillation or when you have a lot of oscillation?
Store more energy.
You have a lot of oscillation because now you have bigger changes in that energy.
Yeah.
You're storing more UG, which creates more kinetic energy. You're storing more US, which translates into more energy. Now, same idea, or take a pendulum on Earth. Situation number one, I have this, okay? Situation number two, I have this,
Whoa.
which takes longer.
Same.
Same.
Why?
Because
So you
it doesn't matter.
Plug in the
Amplitude
height.
is not a factor.
No.
So this was discovered by Galileo. According to legend,
Less.
Galileo was
Galileo
Galileo was in a church, and there was a big like chandelier full of candles, and it would start to oscillate when someone would open up a door. It was windy, it would begin to oscillate. And according to the legend, he would use his pulse to count. And what he discovered was that using his pulse is that as it slowed down, the period of the swing stayed the same.
What if he got excited?
That was Galileo. He's old
Is he
school, man. It's like a
regulating his
whatever,
heartbeat to
you
say
know.
the exact same?
If you're in a church and you're to the point that you're counting swings on a chandelier, you are not getting excited about anything at that point. Okay, trust me. So, and that was one of the things that, according to Galileo, how that played out. So, when you get to number 8, okay, when you get to number 8, you're going to calculate an experimental error. So remember, experimental error is theoretical minus experimental divided by theoretical absolute value of that times 100. So you're going to use the slope of that line as your theoretical value, okay? Or accepted value, same thing. Theoretical means the same thing. And your answer to number 7 as your experimental. So basically, you're going to take your slope minus your answer to number 7 divided by your slope times 100. Okay? So this is the second way that you can find the value of K. So what I want done for tomorrow, go back, get this part done, draw the slope, get through number 8, and that's as far as I want you to get for tomorrow. Okay? And the graphs. So, through number 8 on page 3.
Oh, okay.
Okay?